So hello and welcome back to another video. This time we're going to talk about bio-based versus recycling plastics, and we're going to see how they differentiate each other across the polymer pyramid or the plastic pyramid. I am Pianegonda, and I help medical technology companies to choose the best plastic for their application. We've helped over 30 medtech companies to be more sustainable with plastics. And let's get right into the topic. So what is a bio-based plastic? A bio-based plastic is, first of all, the term bioplastic can be a little bit misleading because bio-based or bioplastics could be bio-based or biodegradable, and we have to differentiate between those two. So in this time we're talking about bio-based plastics, which means that they are derived from feedstock that comes from a bio source. Either it's sugarcane or it's potatoes or corn, stuff like that, which will be first generation. Then we would have second generation or biocircular feedstock, which is something like bagasse, which is sugarcane waste. The waste product after sugarcane has the sugar extraction, or used cooking oil, stuff like that. Good. And you can have biodegradable plastics that are also biodegradable, such as PLA or PBS. Or you can have bio-based conventional plastics. For example, biopolyethylene, biopolypropylene, biopolyamides, and stuff like that. And then you also have the fossil-based versions, which we should not omit. So here are the conventional plastics, such as polyethylene, polypropylene, polyamide, stuff like that. And then what many people don't know is you can also make degradable plastics from fossil sources. So that's also possible. And now we have to talk about the plastic pyramid. So this is a classical, let's say, plastic technology chart that is used everywhere. I don't know who invented it. It's very old. But basically, you have a pyramid, and on the bottom, you have commodities, mass plastics. So polypropylene, polyethylene, PVC are usually put into the commodity or always put in the commodity base. So these are plastics which are used very often, have a very low price, have a very high market volume, and usually their properties they're good enough for what they're doing, but it's not that they have the most stellar properties. They're cheap. They are very often used in things such as packaging or consumables and stuff like that. And their environmental footprint is pretty low. Their price is pretty low, and also their properties are pretty low. Then we have the engineering plastics. So everything where the commodities cannot do the job, because you would always choose a commodity if you can for the requirements. And then you have stuff like polyamides, PBT, polycarbonate, POM, polystyrol, ABS, PET, stuff like that. And these would be used in applications where commodities cannot do the job. They have a little higher price and they have a little higher environmental footprint. They're more difficult to synthesize and they have higher properties. And then on top, like on the pinnacle of the pyramid, you have the high performance plastics, such as the best known example is, of course, PEEK, but you also have PTFE, PSU, PPSU, PEI, LCP. Those are typical high performance plastics. They have extremely high properties, such as mechanical properties, chemical resistance, and they also have a very high environmental footprint because you need a lot of energy to synthesize them. So, and now, I mean, recycling plastics should be clear from the videos I've made. They are recycled, mechanically recycled, and now we're going to compare the two bio-based and mechanical recycled plastics with respect to their place in the plastic pyramid. So if you have, I'm going to explain the chart. So the chart is, we have the product carbon footprint, cradle to gate, very important, cradle to gate. So basically when you buy it from a plastic manufacturer. Then we have polypropylene, which is a prime example of a commodity. Then you have polyamide, which is a prime example of an engineering plastic. And we have PEEK as a representative of the high performance plastic family. And now we have the fossil cradle to gate product carbon footprint, which is for polypropylene, you find different numbers depending on the manufacturer, but usually around 2 kilograms of CO2 per kilogram of plastic. And then you have for polyamide, it's I think the value you find the most is 6.6 kilograms of CO2 per kilogram of plastic for a fossil based. And then PEEK is everything between 20 and 25 kilograms. So very, very high environmental footprint per kilo. And now bio-based plastics, they save CO2 by pulling CO2 out of the atmosphere, transforming it using, of course, photosynthesis, and then using the carbon to build their bio feedstock. And then you transform the bio feedstock into a monomer and then synthesize the plastic from that. So it is saving CO2 by something that is called biogenic carbon. And the biogenic carbon is a credit. Sometimes, let's not get into too much details of how you calculate that in an LCA. There's a certain method where you do count it, where you don't count it, but usually the plastic manufacturers count it as a credit at the beginning of life. So you pull carbon out of the atmosphere and therefore you get the biogenic carbon credit, which will reduce your CO2 footprint around 2 to 3 kilos of CO2, depending on the plastic. So how much carbon you have in the plastic, that's like the credit you will get. And that means that for a polypropylene, you will get below 0 cradle to gate. And that credit is constant per kilogram of plastic, depending on how much carbon you have in that plastic chain. Meaning that you will get a 2 to 3 kilogram reduction, basically independent of the plastic. Meaning for polypropylene, it is a huge saving. And for polyamides, it's respectable. And for PEEK, it's just only 10 to 15%. So the higher up you go in the plastic pyramid, the less percentage you save by saving 2 to 3 kilograms. And then with mechanical recycling, you have basically the opposite. The impact is nearly constant. It's not perfectly constant, but as a model, it's quite good. So you usually, like for mechanical recycling, your environmental footprint depends on washing and depends on sorting your plastic. And that is, and extrusion is also, of course, another factor. And the extrusion temperature plays in to that a little bit. So PEEK is extruded at 400 degrees and polypropylene at maybe 230, 250-ish, meaning that polypropylene has a little less environmental footprint for mechanical recycling than PEEK, but it is between 0.3 and 1 kilogram of CO2 per kilogram of plastic. So it's nearly constant or in that range. Meaning that for polypropylene, mechanical recycling is not better than bio-based feedstock. So you save more by doing it bio than by mechanically recycling it. There are also other environmental footprint factors such as land and water use, but let's not get into that. For the CO2 footprint, bio-based polypropylene has the better the better CO2 footprint than mechanical recycled polypropylene. Then with PA6, we already see the switch. So we have the better saving with mechanical recycling than with bio-based. And for PEEK, it's even more extreme. You can save up to 90% of your environmental footprint with recycling the PEEK than if you do it bio-based. So for high performance plastics, bio-based alternatives do not save you a lot of your CO2, but recycling does a lot. So and like this, you see the discussion bio-based versus recycling plastic depends a lot on where you are in the plastic pyramid and how much of a high performance plastic you have. And that's basically the point I'm trying to make with this. I know it's a little more differentiated than this, but as a first rule of thumb, as a heuristic, it works very, very well. So here we have the points summarized. So bio-based plastics reduce the CO2 footprint via biogenic carbon, which is around 2 to 3 kilograms of CO2, depending on the plastic. Mechanical recycling have a product carbon footprint of, it can be between 0.3 to a kilogram, but like 0.7 is probably also a good estimate. And it largely is independent of the polymer because washing and sorting, they're independent of the polymer source, and then the extrusion takes is a little differentiated between the plastics. Then the preference for bio-based versus recycling plastic depends on the virgin polymers product carbon footprint. The higher your footprint, the better it is to recycle. And the lower the footprint is, the better it is to make it bio-based. For technical and high performance plastics, recycled plastics offer a much lower CO2 footprint than the bio-based ones. And of course, like a comment I got I did the LinkedIn post with that graphic, and the comment I got a lot is that it's probably going to be a combination between bio-based and recycling, which is going to be the future. I of course agree with that. You should take bio-based feedstock, and then at the end of life you recycle, so you make bio-based polypropylene and then also recycle the polypropylene. That's of course a very valid option, and I think a symphony of bio-based and recycled plastics will be the future. So that was it for the video. I hope you enjoyed it. If you have any questions regarding the thing, just put it in the comments. And if you are a medtech company who wants to design your devices for sustainability and use the best plastic possible for your device, then there's a link in the description. You can click that. And then if you like the video, you can like it, you can comment, you can subscribe, because YouTube will show you more content like this, and you will get more videos that you like. Then if you want to request something, a video that you would be interested in me making it, then write a comment. I read all the comments, and I will try to incorporate your wishes into the making of these videos. So thank you very much. It is always a pleasure to do these videos for you, and have a very good one. Thank you.